Thank you everyone for joining us today for this internal seminar. Timon is a lecturer in School of Computing. They're going to be talking to us about learning intersecting surfaces via invariants. Beyond that, I'll leave it to you. Questions at the end, if you have them.
Okay, well, thank you very much for inviting me. So the topic I'm going to be talking about is essentially the research that I've been doing over the past year and a half, maybe two. It started all with a problem in physics, which then turned into a problem in mathematics for us. And then there's to make this actually useful, you require machine learning. So hopefully I can sort of bridge these three subjects for you and sort of show you how they intersect on this research topic. So we'll need a little bit of physics context before we can get to the meat of the project itself. What I want to talk about as a background context is machine learning of interatomic potential. So this isn't actually the topic today, but you need to know a little bit about this to understand where we start with hypersurfaces later on. So what are we trying to do? Well, everything you know is made of atoms and molecules, right? So you want to be able to model materials. In order to do that, you need computational models that are not just accurate, of course, otherwise they're useless, but you in particular need them to be computationally quite scalable, because even just this table that I'm sitting on is comprised of a ridiculous number of atoms and molecules. So if your algorithm even just scales like n squared or something like that, you're not going to get very far with this, right? Okay, so you need to be quite efficient. And of course, you're also usually limiting the scope of what you're trying to do. You're not trying to model the entire system. You're trying to extract certain properties that you're interested in at a particular point. Maybe that's the charge of the system. Maybe that's how it evolves in time, and various other things. You're usually not producing a complete model step by step of the entire system. Simply not computationally feasible at our current capacity. Okay, so how do you actually do this in practice? I'm going to simplify a lot of stuff. Well, first of all, you need a description of your molecular system. So it's comprised of different atoms. They are different elements. So you can have oxygen, hydrogen, carbon, all various different things. They behave differently. So you need to account for that in your mathematical model. Charges, that's actually quite challenging. So electrical charges on the atoms, if something's not in a neutral charge state, that has an impact on the dynamics of the system. And as you well know, even at our macroscopic scale, electrical charges essentially dominate our lives. Positions, of course, I mean, how close two atoms are to each other completely affects how they interact, right? Do they attract? Do they repel? Are they trying to move away from each other? Are they exchanging electrons? All these sorts of things. So these are attributes, and there's many more attributes that one could put in here, and they usually are put in there. Mass, I guess I haven't mentioned that technically. You get that from the elements, right? But that needs to be embedded somehow. Okay, so once you do all this, you end up with a particle description that just sort of mathematically describes your system, your structure that you're trying to work with. And then there's something very classical and highly accurate, is a computational framework called density functional theory. I won't talk about how this works, but basically using density functional theory, you can, for example, for this molecule, which is this chemical formula here, ALA is a colloquial name for it, you can compute its energy states using density functional theory. Okay, we don't need to know anything about density functional theory other than it's accurate and ridiculously expensive to compute. So you cannot do anything meaningful with it other than extract data that you can then maybe extrapolate from, but you're not going to describe the entire dynamics of a molecular system from density functional theory. Simply not feasible. But it helps because you can have a first principles data source, which from a machine learning perspective means if you need more data, you make more data. Now it's expensive to make more data, but you don't need a lab, right? So you can compute it, which makes it easier. Because if you, for example, work in different machine learning fields that are sort of related, that I work in like collective biological behavior, well, you need to get out your cameras and actually go out and record things. It's difficult. Here you have computationally expensive, but doable computational model to compute first principles data. But it's expensive, so you can't really use it for anything particularly interesting. So you want to extrapolate from that data, and that's where the machine learning comes in. And what's usually used here are methods called machine learned interatomic potentials. So interatomic just means between atoms, right? And potentials here is the energy field between the atoms. So you're trying to basically predict the potential energy in these systems based on the potential energy that we know for particular configurations, right? And you can already see how this becomes a sort of really challenging machine learning problem at this level. Because even if we only consider positions, how many atoms are there here? They can all move in 3 directions. So what we have 3n degrees of freedom for a large system. How could we possibly sample that sufficiently to then extrapolate something meaningful from it? And that is somehow the magic of machine learning interatomic potentials, that it is even possible to do this. But to effectively do this, there's lots of tricks that we need, symmetrization and all sorts of stuff that we don't have time for today. But the point is, this is sort of the paradigm from which we start. If you have a description of your system using classical theory, well, nowadays it's classical, but of course, most of this is quantum theory, so it's not classical theory in the Newtonian sense. Using this, we can then train machine learning models which can predict properties of molecules and atoms. And then you can use them to do molecular dynamic simulations. So here is a molecular dynamic simulation of that. It's just this molecule in a particular state of temperature and interacting with different things. The details don't matter here, and this is actually a lot more smooth. This animation is just choppy because of teens. But the point is, previously you could maybe extrapolate states like this one. Now you can actually compute with it because you actually have something that can predict the energy levels in different configurations. Okay, and hopefully it's clear that this is important for all sorts of fields, material science. This molecule in particular has been shown to exist in the human bloodstream. Do you want to know how it interacts with medication like pharmacokinetics? You can do lots of different things if only we can get efficient enough with these types of models, right? And I want to be clear that these are trained on foundational first principles data, right? So they're essentially extrapolating from really highly accurate data. But that's not exactly the problem I'm going to be talking about today. So I've omitted something, which is that, well, quantum physics is quantum, which means that actually there isn't just one state of energy for a system to exist on. When you open chemistry journals, you will often see spaghetti plots like these. And what they are showing is the different energy levels at which a system can exist. The quantum in quantum physics really refers to the fact that the energy systems exist at is discretized. So quantum, as in there's a discrete amount of thing between the energy levels that can be occupied. That's different from classical physics. I can lift this table, well, I could lift it, and there would be a continuous increase in its potential energy as I lift it, assuming that space is continuous. In the quantum physics world, this is silicon, for example. Silicon can simply not exist at all possible energy states. It can occupy discrete states, the bottom of which, so the sort of the usual state it would exist in, is called the ground state. That's the bottom line you can see there. But then there are essentially infinitely many discrete energy levels above it that it could occupy instead. And how you get to those levels, again, these are physics questions, but an example of this is, when light shines on a material, some materials can absorb that energy, and that can elevate them to a higher excited state. Okay, and then they exist in a different essentially different state physically, but the positional configuration is the same. So this is tricky. And you might say, maybe we don't need this. Maybe all we want is dynamics like this for the material. But the problem is these types of diagrams, they decide whether something is conductive, semiconductive, not conductive, right? So if you're talking about the electronic states of systems, this really matters. So you can't even do a rough approximation because, as we'll see later, a rough approximation of electronic states turns a semiconductor into an insulator. So you cannot be drop accuracy on these applications. Okay, but we live in the same space as we did before. Before we were doing like ground states and potentials. Here we're saying, well, there's not just a 3n dimensional energy landscape. There's multiple surfaces that are 3n dimensional that intersect, right? As you can see, at some points these can touch. And those points where they touch, that's particularly interesting configurations and states where essentially all the electric magic happens, where they can move between states freely because the energies of the two states are the same. Okay, so you really care about these so-called conical intersections where these states touch. Okay, so that's the context. We're in a physics problem where we want to figure out these things. We want to really learn these. Density functional theory and adjacent methods allow us still to compute these values, but how do we learn these intersecting 3 n-dimensional manifolds, essentially? Okay, so hopefully you can all see this. Now, how do we even get this data, right? So when we do the density functional theory or cluster expansion, whatever we're doing, how do we receive the data? Well, ideally, this is a one-dimensional problem. We might want to think we get it in this form, right? Now, hopefully we would get points evaluated on these energy surfaces, and you can track where the surface goes as they entangle and cross. Unfortunately, that's not the case. Without going into too much detail, the computation and the physics background of how you compute these requires the computation of eigenvalues of an Hermitian operator, which give you real values, but they don't have an order. I mean, you can order them by value because they're real, but then you get this on the right here. So hopefully you can see now the ground state, for example, has a cusp here. It's no longer a smooth function. Well, because it's actually, what's my cursor there? It actually would continue up there, but that you don't know that. You're just getting at each point 3 values sorted by their value. So you actually have no idea how to track across this. And what does this mean? Try to approximate this with the machine learning interaction potential that we talked about, like the atomic cluster expansion, something like that. You're going to be using globally smooth functions essentially in your machine learning approach to learn these. And what happens, well, it's bad because you're trying to use smooth functions to approximate non-smooth functions. I mean, it's possible, right? But you require a ridiculous degree in your polynomial approximation. Okay, so this is what you want, right? So just to be clear, these are the bottom 2 surfaces of these 3. So we want to predict these bottom 2. Remember, there's essentially infinitely many, so we have to cut it somewhere. And if you just use the conventional methods, well, it's bad. And you might say, actually, that's not so bad, right? I mean, away from the cusps in particular, it looks pretty good. And that's true. And there's a mathematical reasoning for this that I can maybe go into later. But it's the cusps that we're interested in, right? Like I said, this might be a semiconductor here. This is an insulator. This gap matters for the modeling, right? So we need to improve this. This is really bad. And in fact, much worse than it shows here, because this is a 1D problem. You try imagining this in 10, 12 dimensions. You see the degrees to which I went to even get a plot this quality, you can't do at the sort of dimensionality that you want to be at. Okay, so that's what goes wrong. What can we do? So it's something that I think is often not the first thing people consider, but essentially when you do a machine learning approach for a physics problem, often the way that you embed the mathematics and the physics of the problem in your machine learning is all that really affects whether you get an accurate or an inaccurate result. In this case specifically, my point is don't try to learn this. You can, at least with your smooth functions that you're trying to use, which are really efficient and work, you can't use it for this. It just simply won't give you an accurate result. So first we try to find some smooth proxy that we can learn instead. And maybe from that proxy, we can then reconstruct the previous thing. So learn B instead of A. And then from B, maybe we can reconstruct A. And then we can avoid these cusps. Okay, so this is where a bit of math comes in. This is just the algorithm. I'm not expecting that we step through this algorithm now. The key points here are that we will need elementary symmetric polynomials. I'll introduce that in a moment. And we need the concept of a companion matrix. And if you just understand the bits of these 2 concepts that matter, you will understand why this resolves the cusp issue largely. Okay, the first thing is, what are elementary symmetric polynomials? Now, first of all, maybe what are polynomials, right? They are terms like 1, x, x squared, and so on, as well as linear combinations of them. So x squared plus 1 is also a polynomial. The elementary symmetric polynomials of 2 terms are basically all the different ways you can sum and take products of these things. So if you have, I think I have an example here. Yes. So if you had three surfaces, the elementary symmetric polynomials of that surface are just summing them up, taking the three products, so that's 1 and 3, and then sort of like a product sum combination of them. Okay, so you're basically just adding them and taking the products in all the different ways that you differently could. And depending on how many surfaces you have, there's more of them, right? So there's just more variations of these. And if you want to write it explicitly, this is the way to write it. So there's m of these for m surfaces. Well, I guess there's m plus 1 because the 0th one is 1, but that's not very interesting. And then at the start, you have all the sums. At the bottom, you have the product of all of them. And then you have these doublet, triplet, and so on product sums. Okay, what's really the important property of these? They don't care about the order. So in other words, if I compute those elementary symmetric polynomials for the thing on the right or the thing on the left, it's the exact same. Right? So if you add the three values together, they don't remember where they came from. If you take the product, they don't remember where in the order they came from. And importantly, because of mathematical properties that are fairly straightforward to convince yourself of, if there is any underlying order that was smooth or analytic, then the sums and the products will end up being smooth or analytic. Because the sum of smooth things are smooth, and the product of smooth things are smooth. The product of non-smooth things can be smooth, but there's no guarantee, generally speaking. But here there is, because we know there is an underlying smooth orientation for these. So the end result will be smooth. Okay, what does that mean? It means we can learn these, right? Using the classical machine learning interatomic potential stuff, using orthogonal polynomials, really whatever you want. You can learn these surfaces. But now you have a surface that you don't want. You have a bunch of sums and products. That's not what you're trying to learn. So you need a way to go back. So we've learned B essentially just by learning we learned something else, which we can successfully learn. How do we go back? And this is an extremely old result called Vieta's formula, or Vieta, if you know him by that name. And I'm not going to go over his theorem either, but it's a classical theorem. The point is, if you combine the elementary symmetric polynomials, you can reconstruct the data. That's essentially just what that says. Okay, if you have the elementary symmetric polynomials, then if you put them into a polynomial where they are the coefficients and compute the roots, you get back the original values. Okay, we don't need to know the details of this. You just need to believe me that there's a theorem that says if you have the elementary symmetric polynomials, it's possible to go back. Okay. Okay. It's possible to go back, but that going back is a root finding problem. So you need to find the zeros of a function. And this is done using the companion matrix method. So this is essentially the most stable way you can hope to do it. I guess I will sort of just brush over this, and then we can come back if you're interested in discussing this in more detail. But the point is, if you're trying to compute the root of a polynomial, so this is a polynomial, a general polynomial with coefficients A. If you put them into a matrix where the negative coefficients are all in the rightmost column, and then there's just a bunch of ones on the first subdiagonal, if you compute the eigenvalues of that, it's the roots of that polynomial. So this is a really sort of just a clever way to compute roots. And roots are how this theorem computes the original values. Okay, so this is a lot of ones. Let me try to explain this process again using this now. First, you have learned the elementary symmetric polynomials. So we're assuming that you've done that. Now you compute the companion matrix of that Vieta formula polynomial. So essentially, the symmetric polynomials just go into the matrix on the rightmost side. And then you compute its eigenvalues. Okay, and those eigenvalues will give you back the points on your original surface. Again, no order, right? But again, computing eigenvalues. You can't disentangle the curves this way. But that wasn't our goal, right? Our goal wasn't to disentangle the right picture into the left picture. Our goal was to be able to use existing highly efficient machine learning tools to learn the right picture. Okay? And we couldn't do it before. But if you learn a smooth proxy and then reconstruct the surfaces, you can. Okay, so I'm happy to go into more details on the mathematical aspects here. But for now, let me continue. So this is the simple example I showed you earlier. Let's say we have three surfaces. We have we have 3 surfaces, but they're sorted by value. So they intersect potentially, and we need to reconstruct them. You construct the elementary symmetric polynomials at the top, you put them into the companion matrix like I showed you, and there's actually different choices for how to put that matrix together. They have different mathematical properties. So if you really want to get into the weeds, this isn't the best choice, but it's the most clear. And then you compute the eigenvalues. So here's a what is this? This is a 3D example, I guess. Well, the surfaces are 2D, right? The surfaces are 2D, but to plot it, I need to be in 3D. On the left, you have the actual sort of example of how these surfaces really look sort of physically. On the right, you have what we get out of our classical methods. So they are value sorted. It's at a slightly different angle so you can see it. But you can see the green plane on the left is a constant, so it's straight. But there on the right, it sort of starts curving. It's just the topmost layer, right? Where they intersect, it loses track of where that curve goes. And again, this is awful to approximate with smooth functions. So there's not just conical cusps, which are actually really bad. There's also straight line cusps, where, and of course, in 3n dimensions, you can have n-1 and n-2 dimensional cusps. So don't learn this, right? Don't learn the thing on the right. Learn this instead. This is the elementary symmetric polynomials. Now they do intersect, but that doesn't matter because we actually have them and contract them across because we're just taking the sums of all of them. That gives us one of them. And as you can see, they are extremely smooth compared to this, especially where you have these cusps. You can learn that quite well, and then you can reconstruct that one, and you can investigate how the errors behave for this sort of thing. So what I've plotted for you here is the absolute error of reconstructing the original data from this using these methods. The black line at the very top is the direct approach. So I call these Chebyshev collocation and direct Chebyshev because Chebyshev polynomials are used in the learning approach. At the top, you can see the direct method. That's the original thing, right? The thing that I said you're using smooth stuff to learn cusps, and it doesn't really work. You can see even with perfectly accurate data, you essentially get 1 digit. That's not useful. Now the 3 different plots, there's a blue one, an orange one, and a green one. They are different noise levels. So you can still in your first principles data have noise. It depends on how much effort you're putting into computing these things. And it's always important in a machine learning context to also add some noise to your data because it's often possible mathematically to reconstruct from perfect data, but you might not have perfect data. So if we have borderline perfect data, this method actually produces borderline perfect results. So if you have 13 digits accurate data, you can get 9 digits accurate reconstructions. That's not realistic at all, right? But it shows that theoretically the method is sound. More realistically, if you have 3 digits of noise, you get 2 digits of accuracy in your reconstruction, which is notably better than the direct method was with perfectly accurate data, right? So even with the noisy data that you have in practice, you're beating your initial sort of just throw the learning tool at it at the problem. Okay, so this is sort of an idea of how the error behaves. By the way, this is a semi-logarithmic plot. So on the left, the error is logarithmic, but the degree of my approximation at the bottom is linear. So actually, if you're in the perfect scenario, you can even get exponential convergence for these methods. But more realistically, you will level off at your noise level. Okay. Here's graphene. Graphene's a very interesting material for various reasons that are outside of my field. It's a hexagonal lattice of carbon atoms, a single layer. It's called graphite, I think, if it's multiple layers. And if you compute its electronic structure, it has these interesting points called Dirac points, where the intersections under quotation marks are actually cones. So it's a really difficult thing. It's an impossible thing to approximate with smooth functions, right? And when you try to do that, you get the thing on the right. And like I said, this has now turned a semiconducting graphene on the left into an insulating graphene on the right. Even though you might look at it and say, well, to the human eye, this looks pretty good. Modeling wise, this is a completely different object. So again, I'm plotting the first 2 states here. Okay, another thing to note, and I think this is slightly underappreciated sometimes, is yes, this is worse, right? This should be a conical intersection. But what's going on up here? There's no conical intersection there? Why is it rippling here when it shouldn't be doing that accurately? And the answer is even worse than just being inaccurate near cusps. If you try to approximate a non-smooth function with a smooth function, you actually pollute across the entire function. Essentially, roughly, because it's trying to resolve that cusp, other problems happen across. And these are global effects. So you get global pollution if you try to compute this. So even if you have a single cusp in the center, it's going to ripple outward and create less accurate models also outside of that cusp domain. So it's less bad than this, but it's still significant enough for models to care about it. Okay, by the way, this isn't true graphene. This is our reconstruction of it. You can't tell the difference visually, but technically, if you zoom in far enough, there is a tiny little gap there because you can't perfectly reconstruct a conical intersection. Ultimately, it depends on your discretization. But obviously, visually, it's the same as just the real graphene. Okay, and again, we can do some error plots here, and it looks much the same. So it depends on the noise that you're putting in. And if you're interested in how the noise translates to errors, the answer is essentially away from cusps, it's linear. So it's as good as you could possibly hope. The noise in the data just translates into noise on the output. Near cusps, you have degeneracy, and your error scale is like the square root of your error. And this is a fundamental part of the polynomial reconstruction that we're doing here. So if you do a root finding problem and you're perturbing the polynomials, you get square root error, which is bad, by the way. Right? It depends on what you're doing, what kind of order you want, but you don't want square root of noise as to be your error, because that means, of course, that you need to be quite accurate before you see gains. That would normally be a big problem, but it just so happens that the model we're competing with is really bad. So it still looks very impressive, but there's definitely more to do in trying to maybe find a different embedding approach that doesn't scale like this near the cusp. If that's even possible. It's not possible with polynomials. So someone would have to come up with a different approach to this because polynomial root finding inherently has that error rate. Okay. This is what it actually looks like. Right? Everything I've shown you is smooth functions. Data looks like this. So this is the actual scattered data that we get for, I think this is SO2. So the molecule is up, you can see up there. And I think this is just, so again, on the left is our reconstruction, and on the right is the sort of direct approach reconstruction. I'll zoom in a moment, I think. But what are we even looking at, right? These are thick outlines. It's because these are higher dimensional things. Think about that SO2 molecule. Well, at the very least, I could change the angle, right? I could change this angle theta here, and I could change the distances d2 and d1, and that's 3D. That's already 3 degrees of freedom that I have there. So even if I take out rotations and stuff like that, because they don't really affect the molecule, these are higher dimensional objects. You literally cannot plot them. So I have to project them down. So this is three-dimensional surfaces projected into essentially a 1D plot. But you can see where the cusp is. If you can sort of just squint at it, you can see that this curve actually continues up there. Right? This is a cusp here. And this green curve continues into this orange curve here, just looking at the bottom edge of it. And you can see in the direct reconstruction that there's a gap. So this has been smoothed out. Right? So it's the same problem that we saw before, except now we're looking at it in the actual data of what you would get out of your approach. And I think I have a zoomed in version on that specific cusp. This is what it should be. And this is what you get when you do a direct approach. So it smooths out these sharp edges, but they are actually there, right? That's where the interesting stuff happens. Okay, and this is an actual application, and this is our actual reconstruction of this edge, and this is noisy data. So the noise level here is at about the 10 to the -2 level, so 2 digits accurate data, and still you move from this to this. Now, you might still want it to be even more accurate, right? But it's at least a big improvement. Okay, there are limitations to this. A big limitation, as I've presented it, is I've said nothing about the fact that when you have infinitely many curves that you are sort of stopping at some point, what if you removed one and then introduced a cusp there? I mean, it could still intersect with the one above it, and you've stopped there. So there could just be a hanging, we call these dangling cusps. There's no reason there can't be a dangling cusp. In fact, you look at the literature, there's almost always one. And as I've described the method, if you compute this elementary symmetric polynomials now, so say you add them up and get the first elementary symmetric polynomial, well, the cusp's still there, right? I mean, it didn't go away because you don't have the thing that matches it. So what happens then is, as you see on the right, so the direct method again is the method without a sort of reconstruction approach, and the Chebyshev method is the best version of our approach. It's still slightly better, but you get nowhere near the convergence rate that we saw before. So you sort of flatten out immediately. And this is expected because again, trying to approximate something non-smooth with something smooth. So you obviously this method struggles more than direct method because it has all these cusps still. But our method still sees one cusp, and that one cusp, like we said, pollutes. Yeah, you have only one, but it's a global method. It will pollute across the entire thing. Now you can actually resolve this. So we have an upcoming paper that basically modifies the method to account for this. And it uses an approach that I think is in general quite natural. It runs the method, it identifies dangerous areas, basically, and then it isolates them and learns those separately. So that way it can treat these cusps. So run the method once, you'll get an inaccurate model, but a pretty accurate one. We saw earlier, right? What you get out, you get it smoothed out. But then within some margin, you can say, mark all of the things for me that look like they could be cusps, and then treat those slightly differently. And you can then combine it to still work. But yeah, there's also some other approaches to this. You could try to just add something on top to match that. It starts to be complicated. Okay, I think I should also at least mention, because I feel like this might be a natural question that people ask. Why can't we just track the derivative? If you track the derivative of the functions of the surfaces, you can identify where it's going, right? I mean, there will be a jump in the derivative if there isn't, like it's not defined at the cusp. And on the other one, you have a smoothly defined derivative that you can track across. The problem is it's always easy to say that in 1D, but in 3n dimensions, in what direction are you computing the derivatives? You need to start thinking about directional derivatives. How do you target the right points? It gets messy really quickly, aside from the fact that you really usually don't want to compute derivatives because the data you need to learn those is expensive to compute. It's possible, and derivatives are a thing that people use to sort of disentangle these things, but you need to be quite low dimensional for that to be sensible, whereas our method doesn't really care about that aspect. Okay, there's some other limitations that yes, so I'll just say them here. There's another big limitation, which is you saw that the last elementary symmetric polynomial is a product of all terms. Well, that's a problem because just imagine it's a polynomial. So simplest possible case that these plots are all just intersecting polynomial curves. They have some fixed degree. Okay, but now we're taking the product of all of them, the degree shoots up. So in other words, I need much more resolution to be able to resolve that last elementary symmetric polynomials. The oscillations can be enormous in that thing. If the initial thing was oscillatory, then the elementary symmetric polynomial will be even more oscillatory in the orthogonal polynomial components, and thus this is a problem. Now, it's a computational problem. Mathematically, it's whatever, it's fine, right? We just increase your degree. But practically speaking, when you're computing 3n dimensional surfaces, you're not going to be using very high degree polynomials. So it can happen that your product ESP sort of slips out of your resolution, and then it can break down. It's resolvable. It's easy to notice that this has happened, but computationally speaking, it's an unsolved problem at the moment. How do you scale this to not just 10 intersecting higher dimensional surfaces, but let's say thousands? You cannot really do that with this method at the moment. Okay, so just maybe to go over what I've talked about, the method I've introduced is basically learning smooth invariants, and these invariants are proxies for something we're actually trying to learn. in order to reconstruct multi-surfaces. In general, the underlying mathematical problem is how do you sort of relearn intersecting surfaces, right? This could appear in many different scenarios, not just specifically physics, but how do you reconstruct these? And it turns out you can do it with smooth invariants. There's different invariants with different advantages. I didn't go into that, but the elementary symmetric polynomials are just one of them. But all of the ones we so far looked at are polynomial invariants, so they are essentially equivalent up to some, some improved numerical behavior. But if you wanted to, you could construct invariants that are non-polynomial, and maybe then something interesting starts happening. We are looking at this. And also, I guess I didn't mention this, but this is, I think, is also very natural. We should really be doing active learning here. And what do I mean by active learning? I mean, when I've computed this, and like I said, I made my first run through, and it says, oh, here and here are danger zones. This could be a cast. We have a way to generate data on the fly in classical methods. So why don't I just say, I don't have enough data at this point, go back to the DFT or whatever you use to compute the first principles data, generate more data, and then sort of retrain near that cast, right? So in other words, this should be active, where we sort of feed back between the physics simulation and the machine learning approach, because unlike in a lot of machine learning applications, we can first principles compute it, right? So it just makes a lot of sense, I think, to say that we are interested in the cusp, find the cusps, request more data near the cusps, right? That's just a natural way to do it. And in early testing, this does behave quite well. It makes it way more expensive because you usually want to batch this, right? You don't want to send an individual point back to the computation. But I think that's a natural way to use learning approaches here, and it's while we've experimented with it, we haven't published anything solid on that aspect yet. Okay. And if you want to know more about this, the write-up is in this paper called Parametrizing Intersecting Surfaces via Invariants. And here's just a neat reconstruction of graphene spinning around. You can see the Dirac cones essentially touching on those points. And again, if you want a smoother version of this, you can see my website. It's only choppy because of the compression. Okay, and I think I stop here, and I'm happy to go into more detail about any particular aspect if you're interested.
To our speaker, do we have any questions?
Yes.
How are you generating the synthetic data, so these things, and why is it expensive?
The synthetic data, or the I mean synthetic in the sense that you're not experimentally measuring.
Yeah, so the sort of the clean.
It's essentially first principles quantum physics equations. Yeah, so there's some slightly, there's some numerical algorithms to make it more efficient, but de facto it's solving quantum physics equations.
So that's a PDE solution, isn't it?
This specific, this is the Hamiltonian of graphene. You can actually make it explicit. So that's why I can plot it so smoothly. The data looks more like pointwise. It's pointwise evaluations. You can solve it at a particular point, and you get the energy levels at that point. Yeah, so you could, I mean, if you've ever seen, that's not how it's computationally done, but you could just solve Schrödinger equation for multi-electron systems. Computationally, it's called DFT, density functional theory, which basically does what I said. But yeah, it's a bit too physically involved to explain, and I would need slides for it. I couldn't just write that on the whiteboard. Yes.
How long does it take to train your model if you're on about this active learning where you rejig, so you train your model, find points where there's problems, go back again? Would that take an absolute age to do, or would it be quite quick?
So definitely I would say that the reconstruction part becomes negligible in that discussion then, because the reconstruction part is relatively fast. So for example, if you use MACE or ACE for this atomic cluster expansion, these are really fast methods compared to the DFT computational cluster expansions that you need to do to compute it actually. Yeah, it would be significant. Let's say you're looking at moving from hours to maybe a day or two if you want to do sensible active learning, which is why I say you need to batch it. You're not going to push individual points to that physics simulation. You're going to first characterize all the points that you want more of, and then probably even overdo it because you don't want to like go back to it that often. But the good thing is once you've computed it, for future runs, you still have that data. It's not like you need to discard it and actively learn in every single run. Yes.
So following on from that, so is it relatively easy in the DFT to say, I want more data in this small area then?
It's okay, I guess.
Yeah.
It's not. I wouldn't say it's possible. Yes.
Right.
Like, you can specify
Yeah.
point evaluations. Yes.
Yeah. And then another question again is kind of, I guess, more for chemistry, which I think we're a little about. But so in terms of knowing if it's an intersection or it's just like two cusps very close together, usually a chemist doing that because of they know a specific substance or they know from other theory that it is a semiconductor.
Yes.
Or
both happens.
right. So, but from the DFT alone, is it possible for them to work out whether it's two cusps close together or it is?
So chemists
Actually,
certainly have worked it out.
Yeah.
Whether you can do it sort of formally is a different question.
Right.
But you're trying to do more than just say there's a cusp there,
Mhm.
right? When you do molecular dynamics or something like that, you're trying to quantitatively predict the behavior of that molecule. So if it comes near that cusp, you need to update its properties and its positions. And how do you do that? And if you don't have the sort of the data to determine its path, then even if you know this is a semiconductor or whatever, you can't resolve that quantitatively. But yes, I would say chemists have figured out a lot with much worse models than even the direct approach. So I think it's just when you start to be quantitative that you want to say, okay, I need to actually know not just that it has a cusp, specifically how does this behave? How does something approaching that energy level, that sort of that domain, how does it behave in the vicinity? And that's why you need accurate reconstructions of the cusp.
So you think that this method would have a lot of potential for material discovery?
It does, but I think the key aspect is, even though it is much more accurate, it is computationally still quite challenging to use it for large systems. Because like I said, the more surfaces you want, the more computationally expensive the degree becomes. So I would say, while we're quite excited about this, we are also not saying that this immediately resolves the problem, because it's just much more expensive still than just throwing smooth functions at it. And depending on what you're doing, that might be enough. But we're viewing this sort of as, okay, look, if you learn an invariant instead and then use it as a proxy, it's much better. Maybe we can find something that's a bit more clever than just sort of these specific invariants, and then it can scale better. So scaling is still a concern, but yes, in principle, if you wanted to learn about material properties of at least small molecules, I think this already beats the current methods quite handily. If it becomes larger, I'm not so sure it can apply.
You've alluded to some molecule, like you said that graphene had an analytic solution.
That's my understanding. So I'm not a chemist, but my understanding is the Hamiltonian is basically computable for graphene.
Is it just based on the elemental composition, or are there other elements that make it more or less
I think
challenging?
graphene is just easy. I mean, okay, again, I need to clarify. While I have a background in physics, I'm not I'm not a molecular physicist or something like that. But it's my understanding it works for graphene because it's a single layer of crystallized, essentially fixed lattice point carbon atoms, where you can make these sorts of computations. If you're talking about graphene more generally, if you want to also bend it or something like that, I think it starts to not work. I think the Hamiltonian is for the specific sort of configuration that's really symmetric and neat, where I assume the equations just work out quite nicely. Generally, you can't do it. So for any interesting material, I mean, graphene is a very interesting material, but for any more sort of complex materials, you can't explicitly compute it. I think there's also questions in the chat, but I'm happy to.
Is there a reason that polynomials were always used as a baseline approximator?
It's just because the numerical analysis of them is very well understood. And so you want to approximate functions, your first graph's probably polynomials. I mean, depending on your field, you might call it Taylor series, or you might do an orthogonal polynomial expansion, but polynomials are widely used to approximate things. You don't have to. I mean, there's nothing inherently stopping you from using different functions. But how would you? I guess you could use splines or something that would be only piecewise smooth or something. But it starts to be tricky, right? How do you feed that into a machine learning algorithm that's trying to extrapolate beyond its scope? So I look at this molecule here. When I plot this data here, I only have very narrow range. Like look at the angle between 1.6 and 2.3 is where all the interesting stuff happens. But you don't know that ahead of time. So you're sort of sampling this space. You're trying to resolve a sort of a big thing, essentially. I'm not sure that anything other than polynomials will work because you lose so much information if you use something like piecewise lines or something like that. But I think the community is open to better methods. I just think we haven't found any. So it's all orthogonal polynomials pretty much.
Yeah, just thinking because like given that you know that there are discontinuities on non-solutions.
Yeah, so what you could
Seems
do
like
maybe, what you could do is maybe use polynomials, identify the critical regions, and then do something else there, right? You could do that. But how do you get the sort of first guess of where the cusps are? You can't place, you can't place a breakpoint there if you don't know the cusps there. So it's sort of like, how do you first get it? Not entirely sure, but we have thought about different ways to embed this entirely. Yeah.